This is actually a picture of the 2-4-8 game or whatever it's a power of 2 game, that's what I call it. But you can pick it up on any one of your apps, and it has some abstract algebra structure on it. My son loves to play. He heard someone give a talk on it at the MAA local meeting, and he just loves the game itself, and he taught my 2 younger girls how to play the game. They sit around and play this game, and I have no problem with it. Go ahead and enjoy yourself. So I just wanted to show that to you because these, I call them flip shift games, have a lot to do with permutations. And there's a beautiful paper someone wrote from our department here on flip shift games and permutations. So it has a lot of algebraic theory. So where are we in Fraley? So I've diverted a little bit from Fraley. I want to keep that track actually. But I am following the Fraley book order as a guide. So we're on finishing section 8. We're skipping section 9, and then we're moving to section 10, which is Lagrange's theorem. Lagrange's theorem is beautiful. It's a beautiful theorem. So I recommend reading these sections so you can get the dry version, because the book is the dry version. It just has, it doesn't have like why these things are important. There's one thing I'll have to say though about the Lagrange's theorem in Fraley. He has a very nice example in the book, and I really recommend looking at it because I didn't put it in the lecture notes, but he has how he's modding by the cosets, described by color coding, dark gray and different shades of gray in that original picture, so that you can actually see what he means by modding out by entire cosets. And that one picture is why I selected this book, because he has a lot of visual in there where you can see these things. So I recommend reading that on your own. It's a good idea to do it. So I started doing some of the homework solutions so you could see them, but I don't think, like talking to you offline, I didn't think there was an issue on working any of the problems. Is that correct? They should have just been standard calculations, but they should also been insightful so you can see something. So they had questions about whether composition of 2 rotations is always it's always a rotation, and you can see that by looking at the Cayley table at the right part. Composition of a rotation and a reflection, that's that little square rectangle down there. You can see that you always get a reflection. Composition of 2 reflections, well, that's that piece right there. You always get a rotation. And then they ask you which elements can be written in the form of R1 to the I, R1 to the J. So I just wanted to show you the permutation description. That I see this better symbolically than I did in the actually looking at the rotation of a triangle. So these are the description of the little r1 and little r2 and little r3 and r1 and r2 using permutations. And really I don't need the 1, 2, 3. I can just write it as just without the 1, 2, 3. It's implied that the first position is where 1 goes to, the second position is where, and these represent the vertices. So I explained that earlier. And then I can calculate the different powers. And what you notice right away, which we played around with D3 quite a bit, you notice right away that when you cube the first rotation, you're back to the start, and that R1 squared gives you R0. And so you can do the computations, which I think from listening to you, I like the feedback over the weekend. It's nice to see people working on abstract algebra. But from the feedback I got from you, I felt like everybody was comfortable with these calculations, and you get these different representations of powers. And the answer is all of them can be represented this way. And does anybody need explanation of how I'm using this symbolic method of calculating the composition? I believe that on the test there might have been some confusion of the order of composition. So in composition, if you're taking F composed with G, you apply G first, and then you apply F. So when you do a permutation, for example, you would apply the inner one first, and then apply the outer one. So that's the order. So you take, for example, to do little r1 squared times r1, or composed with r1, you start with r1, 1 goes to 3, and then go to little r1 squared, which is right here. 1 goes to 3, and 3 goes to 3, so 1 goes to 3. That's the order that you do it. No questions on that? You know what I realized? We are moving fast. We're on section 10. And I look back where I was the last time I taught this, all by Blackboard. It's because we're doing the PowerPoints. It's moving fast. And I realized that because on Wednesday I taught pre-calculus. Every time I teach pre-calculus, I do 10 problems, 10 pre-calc problems, which doesn't sound like a lot, but with the Blackboard I was only able to do 4. So I'm smoking with them. I'm already more than halfway through the class. But the thing is that your high school teachers, they're keeping up because they have the videos to watch it and replay it, so they are keeping up. I feel a little guilty when I saw that. So ask me questions, or else we're going to just move on to section 11. We'll finish the book. It'll be the first time anyone ever has finished the book in graduate abstract algebra. Because this used to be 2 classes, 2 semesters. Okay, next one is if t is an integer, can r1 to the t r1, little r1 be written as little r1 times composed with r1 to the j for some j? And what you should have realized from just direct computation is, so I did the computations here so I could compare the two. And what you should have realized is you get something like whatever this t is over here, you should get 3 minus t over here. And that's just looking at the patterns. You guys just nodding because you're agreeing or you're falling slowly asleep? Everybody's looking more and more tired as the semester wears on. The good part is this semester will end, our semester will end in May. So you have a few months with your school still going on without this on top of it. Question, Ted?
You know, I got t equals negative j.
It's the same thing, right? 3 minus t would be, right. Rewrite table, I just did, right? That was all my scratch. I just rewrote the entire table symbolically. Then working with the matrices, you get if little r is minus 1, 0, 0, 1, it's easy to show r squared. These were simple once you started using the matrix multiplication. And you get that order of r is 2. So again, that problem, I wasn't sure what they wanted to do. I thought they wanted to guide you somewhere with a composition of 2 things. And I think Jeff pointed out maybe they meant that you should show it's not equal. So there's no way that you can get one of them equal. That could be the case. I'm going to write the authors directly and let them know that there's a typo. And make sure that that's what they wanted. Okay, so the first homework problem, this is how I'd like to do the homework this week if you're open to it. I would like to do it as an in-class assignment, which you won't be meeting in class on Wednesday, but I welcome you to share. I don't know if you guys can start an online discussion on Canvas. Can you start an online session on Canvas, or does it have to be the instructor?
I think it depends on what permissions you have selected.
Okay, let me check into that, but if all else fails, you can always use Skype. Or even you can use any chat program, so you can type to each other and then take pictures of your work. So you can still do group work, and I encourage you to do that so you can cross-check answers with each other. So you can still turn in one in-class assignment with 3 people's name on it if you want to. That way you can work together and get the insight, because I think you learn a lot from doing things together like this. So here's the question I had. I'm trying to introduce you new groups that you might not have seen before, but are really interesting examples. And this group is called the group of Quaternions. So the group has this presentation, and the whole purpose of this problem is to get you familiar with the idea of a presentation. That it's not just enough that you have one element, that it's powers of that one element that gives you the entire group, but instead you have here 2 elements generate the group, in this case of Quaternions. You have an A and a B, but with these restrictions. So it's like those logic puzzles that you put together where they give you some constraints and then you try to come up with the full picture with those constraints. I'm thinking of these kind of logic puzzles where they say, you know, someone has labeled 3 jars, mislabeled 3 jars, and they give you some criteria about the jars, and they ask you to correctly place the labels on the jars. It's the same kind of thought process that goes into creating the Cayley table. Some of you are nodding, so you know these logic puzzles. Huh? Oh, really? I would have a lot of fun with that then. But it's time constrained, right? So I don't believe in timed tests. Unfortunately, I'm constrained by the university policies, but I don't believe in time tests. I like to have free thought, as long as I want. Okay, and the last part of this homework problem. So the first part is just to show that you're going to get distinct elements from these calculations, which means that you know what the size of your Cayley table is going to be, because these are the distinct computations you're going to get, and then create the Cayley table for this group. But you can also look at this group with a matrix representation. So if you let little a be that matrix over there, and little b be this matrix over here, where I is the complex number I, then you can show that A and B satisfy all these restrictions up here. So indeed, you can discuss the group of quaternions in terms of matrix multiplication, which is always a cool thing, because we know how to multiply matrices, especially 2 by 2 ones. Nice, right? So if you have students who say, what are we ever going to use matrices for? Well, wait till you take graduate abstract algebra. You'll find out. Keep going. Do you guys get those questions?
They don't like when I say to do math later, though.
You know what? It's interesting. I asked Calc 1 why what reason they're in Calc 1, and many of them put because it's a prerequisite for Calc 2. And math majors put this, no less. So we were looking at that data, and my colleague says, I wonder what happens when they get to the final math class. I needed to graduate. Yeah. So that's called the Quaternion group, in case you wanted the spelling, which I'm a bad speller, so I probably misspelled it. That's the problem with the tablet. It doesn't have the spell check on it. So this Quaternion group is used in applied math somewhere. I feel like I've seen it somewhere. Ryan, you want to get your PhD in applied math? Why don't you dig up for the history of this thing?
I've seen it somewhere.
Should be easy read, right? Why don't you look see if it's applied anywhere? I feel like this came from an application.
I think it has something to do with 3D vectors and space.
Something, yeah, it has something to do.
I remember for 3D programming, if you're working in like a 3D world, it's easier to do the matrices with quaternions than it is to do the vectors. But I forget why. So
And I feel like somewhere I've read a history that this group came out of the application. It was not invented by a mathematician to torture students, which some examples are exactly that. So I think this came from an application. There's some really other nice applications if you're interested in applied math of these groups, not particularly these groups, but some groups. We used some in PDEs last semester, but we have seen these groups in what we call the n-body problem. So the 3-body problem is the Earth, the Moon, and the Sun. And there's group structure and symmetries that are existing in those different 3-body problems, but you also have in the n-body problems. So you see another example of group stuff. Of course, I focused on this most useless application, which is games. Okay.